Thank you all.
Yeah, thank you very much. I have the pleasure to introduce to you Professor Takayoshi Kobayashi from the University of Tokyo. He's currently Professor Emeritus at the University of Tokyo and has a very long and successful career. So he studied physics and did his bachelor and master degree and even his PhD at the University of Tokyo between 1962 and 1972, then became a senior researcher at the Riken Institute, the well-known Riken Institute, and in 1972, between 1977 and 1979, he also joined the Bell Labs in the United States, and since 1980 to 2006, he became the professor of the Graduate School of Science at the University of Tokyo, and in 2006, he obtained a chair at the National Chiao Tung University in Taiwan. Since then, he has been appointed as a professor also at the University of Electrocommunications in Tokyo. He is a guest professor at Tokyo University of Science and also a guest professor at Kanagawa University. During his career, he has researched many different fields. For a very long time, he has been involved in the development of ultra-fast lasers and ultra-fast spectroscopy. He was involved in research on quantum information science and technology, and over the last 10 years, he has been also involved in the development of photothermal super-resolution microscopy techniques, mainly with applications in biological and medical research. He has published over 600 original papers and 300 review papers and obtained quite a number of awards. I may just shortly mention that he was awarded for his outstanding contributions by the Japan Minister of Education, Culture and Science. He obtained the Humboldt Award for his outstanding research in the development of ultra-short pulse laser and ultra-fast processing molecules. He obtained awards of the Japanese Chemical Society. He is fellow of many different societies across the world. So we are very happy to present to you his contribution to photothermal microscopy and spectroscopy, which he has recorded.
So yeah, I will share his recording just to mention that please optimize your volume. So if it's, it's not proper.
Okay.
And he will be also able to answer questions after his recorded talk. So I will share his recordings.
Yes, please.
And
I'm going to talk about the development of multicolor multimodal microscope. My talk is organized in the following way. After the introduction of multimodal imaging, super resolution and high sensitivity, the example of this new method applied to mouse brain and mouse skin cancer are to be discussed. And also another type of multimodal microscope called SEIG is also introduced, and microscopic image analysis of mouse skin cancer and statistical analysis of mouse skin cancer are to be discussed. And I'd like to summarize at the end. Advanced features and the principles of the developed microscope are listed here. Multimodal, the first advantage is multimodal. There are 4 modes. The first one is stimulated emission modes, SEIG or stimulated Raman gain. And the second one is fluorescence intensity reduction by stimulated emission, we call the cipher. And the photothermal microscope, which is the main subject to be discussed in this talk, and stimulated emission lifetime called SLIM. And beyond diffraction resolution, this is the pump probe microscope. Then the signal is proportional to the pump time probe. Then in case of in space domain, this this feature is useful for obtaining super resolution. And also we developed new types of circuit noise reduction by auto balance or time division balancing or space division balancing I'm going to talk about. And we can obtain electronics which can reduce the noise level substantially. Symmetrical color method, this is pump again the relation, proportionality relation of signal being the product of pump times probe in time domain. Then by modulating the pump and probe at different frequency, then you can detect the bit frequency or some frequency of having with the signal can be locally detected in time domain. Simultaneous multicolor can be obtained. Multimodal imaging shown here. Stimulated emission-induced gain, SEIG, and cipher emission-induced fluorescence intensity reduction imaging is shown here. Here shows the Jablonski diagram of electronic state of molecules with several excited electron state S1 to Sn, and internal conversion takes place after photo excitation to the Franklin state, and then vibrational relaxation takes place even from the lowest electron excited state to the equilibrium state from the Franklin state, and then the some spontaneous emission takes place, and then even the pump probe configuration, then the excited state, electronic excited state can be dumped via stimulated emission induced by probe light. And then the gain of probe intensity, probe by stimulated emission, we utilize as a SEIG imaging. And fluorescence intensity decrease due to excited state depletion cipher. And side positive effect is this observation may reduce photo damage because of the energy stored in the excited state or vibration state, then it is dumped via the stimulated emission process. For the summary imaging, this main subject to be discussed in the present talk. In this case, no requirement for fluorescence material. The principal PT is for the summary effect induces a concave lens, and then concave lens may deflect the probe light by the effective concave lens. And then the change can be sensitively detected, and sample temperature increase of about degree or so may induce refractive index change of 10 to minus 4. And then this is an example of label-free image of rat skeletal muscle. We can see clearly the PT image in comparison with the transmission image. For the thermal imaging is shown here, 3D imaging of malignant melanoma. PT image and transmission image are shown here. And in case of PT image, you can clearly see the higher resolution, spatial resolution observed in this area, as can be seen. Different in shape and distribution of melanin globules between benign and malignant tumors. Histopathological inspection is not recommended because of the danger of the cancer area extension upon surgical removal. Succeeded in high-resolution 3D imaging of skin cancer without surgical removal, and it can provide reliable and safe diagnosis. PT imaging can also be applied to the three-dimensional configuration, 3D spatial distribution of the malignant melanoma fitted with log normal. And this is useful for studying the cancellation mechanism from this distribution of the melanoma. PT, the image of mitochondria in skeletal muscle of live blood after ischemia is obtained. And this can be applied to the sports medicine. For example, then just training, then muscle is developed. During this process of utilizing live mat, we could observe the change of the muscle structure as shown here. This is 15, 20, 25, 30 minutes after ischemia introduced by the forced training of live rat. The multicolor PT imaging, another example is social component analysis by multicolor imaging. This is the sample is stained with hematoxylin and eosin stained ovary from rabbit, shown here. They have different staining dye. Then we can separately distribution of the colored stained region of in this system. PT, this is the multimodal imaging of PT plus fluorescence imaging. Fluorescence is optical imaging in pathological process, in this case, Alzheimer. And successful simultaneous optical imaging of amyloid beta and glia cells. From this image, more successful simultaneous optical imaging of amyloid beta and glia cells, we could find more concentrated amyloid beta near glia cell. Function of glia cells are well known. The first one is the whole neurons in space, named after glue, and supply nutrients and oxygen to neurons, and destroy pathogen and scavenge dead neurons killed by Alzheimer process. And reactive atheroglycosis is a defensive brain reaction in terms of isolation of the damaged area from the rest of central nervous system tissue, and also reconstruction of BBB and remodeling of brain circuit in region. This is in collaboration with Professor Iwatsubo from the University of Tokyo. This is from this amyloid beta can be measured, obtained, and also for thermal we can detect the glia cell. And model mouse for Alzheimer's disease was developed by the group of Professor Iwatsubo in the University of Tokyo. And accumulation of amyloid beta, multimodal optical imaging of pathological processes, injury, infection, ischemia, degenerative disease of neuron, astrocyte changes to reactive astroglia. In this case, then the neurite elongation and neural cell body hypertrophy take place, as shown here. This kind of histological change can be detected in our Alzheimer disease-induced. This is specially prepared Alzheimer disease introduced in model mouse, and we can see this star-like structure. This is astrocyte, activated astrocyte, and then this change, this kind of physiological change takes place. Physiological or pathological change takes place. Super resolution is also another advantage of our method. Observation of pump probe microscope, then conventional microscope focal plane here, and then space transfer function is shown here in terms of normalized spatial frequency and transfer function value. And in case of conventional microscope, this is the very limited spatial frequency. But in case of confocal, then confocal case, one aperture unit, then it is extended, and even more with zero aperture unit, then the confocal microscope can extend. But zero aperture unit means there's no transmission. So then but pump probe correspond to the best case of confocal zero aperture unit, even though it is, of course, there is aperture, but still it is corresponding mathematically. It is corresponding to the confocal microscope of zero aperture unit. And PT imaging of 20 nanometer single gold particle is shown here, and pump intensity distribution and probe intensity distribution, and PTM is becomes narrower than PTM signal, become narrower fluids have maximum in XY direction. And resolution enhancement by illumination can be obtained in case because we are taking advantage of again pump probe configuration. The signal is proportional to the pump times probe. Then in case of ring aperture, then it gives some kind of circular ring, diffraction ring, and because they have different color, then they can have different fringe ring diameter, and then product of the two becomes, as can be shown here, point spread function becomes narrower at the central part, and also the fringe ring intensity is very much reduced. And in case of circular aperture and ring aperture case, then circular aperture case, fluid have maximum is 230, but ring aperture case it's narrower, much narrower, correspond to 160 nanometer, and from calculation, resolution in terms of fluids half maximum is given by this equation with A being constant. In case of conventional microscope configuration, 0.51, and PTM case circular aperture 0.36, and the ring aperture case PTM 0.28, and the resolution enhancement by nearly 2. Actually, the ratio is 1.82 times the enhancement. Resolution enhancement can be obtained in this configuration. And this is an example, not only XY direction, but also depth resolution is also enhanced. And as it can be seen, in case of circular aperture, inverse ring and circular aperture case, then you can see, for example, the cross-sectional intensity distribution along this dashed line shown here. This is circular case is black, and the inverse ring case is this red color. Red color shows much narrower resolution, much better spatial resolution can be obtained. Also, we calculated the point spread function vector field theory utilizing this. Not only XY but also XZ depth resolution can be enhanced nearly 1.4 to 1.8 times better than the conventional microscope in 3D direction. And high sensitivity is also obtained by signal to noise ratio improvement with auto balance detection system, ABD. Schematic of pump probe microscope is pump and probe and modulated pump, then rocket detection to detect this kind of change of the light transmitted through the sample 10⁻⁵ to 6. But in case of we can remove the common noise in the signal and reference by this auto balance detection system, then just adjusting this subtraction factor G, then we can reduce the noise substantially, as can be seen in the example with avalanche is auto balance detection system ABD with and without. Then in case of without ABD avalanche auto balance detection system, then the there no image can be obtained, can be seen. However, in case with the use of ABD, then we can see the clear structure. And space division balance detection also utilizing the subtraction circuit. Because of this configuration, then the probe light pump probe for thermal imaging, then probe light is deflected out to the outside area of the sample. And then in case we can subtract this one, then we can by for thermal signal S plus laser intensity noise can be subtracted by this subtraction circuit, and then we can obtain the with SDBD space division balance detection, we can enhance the signal to noise ratio about 4 times enhancement. And time division balance detector for noise reduction for broadband continuum is also attained. And we reported this new circuit in this literature, and the characteristics is a common detector for probe and reference are utilized to subtract the common noise, and probe reference gain control by synchronous signal phase, correction of the branching ratio, and the feedback control dynamic correction of intensity difference between probe and reference can be obtained. For example, the example is shown here, simultaneous Raman image of plastics sphere beads. Then we can enhance the 12 times signal to noise ratio, as can be seen from this level to this level with noise cancelling. And multimodal imaging of mouse brain is shown here. Fluorescence and PT imaging of cortex form mouse, and this is PT and FLYFP and overlay. From the overlay, we can obtain the green part is YFP confocal neuron, and red label is PT, and the orange part is the overlap range of green YFP and red label. And then from that, we can obtain this kind of 3D image in volume of 20 by 20 by 16 cubic micrometer. And then the red photothermal is due to glia cell, and confocal green fluorescence is confocal imaging. And then some domain, we can simultaneous imaging of neuroglia vascular unit, PT plus confocal fluorescence. And then neurons, glia cells are cerebrovascular cells, occupies full brain volume. PT image read exclusively against neuron green part and vascular cell red part, and red spots are due to glia cell and probably mainly feet of astrocyte. And BBB area can be detected blood-brain barrier. And then by utilizing this multicolor imaging, we can obtain the area, the glia cell is accumulated near the glia cell full brain volume and PT image exclusively against neuron and vascular cell and mouse. This is from mouse hippocampus and simultaneous image of neuroglia vascular cell. And this type of PT image mouse brain slice shown here, and this is here shows the 600 by 600 times by 30 pixels. And stimulation emission induced gain microscope SEIG. And principle SEIG is discussed in the previous view graph, and we can utilize stimulation emission for imaging. And SEIG stimulation emission induced gain image of biological sample is shown here, and mouse mesenteric lymph nodes are shown here, and we can clearly see the structure here. In case of without node reduction, it's not possible to see, if any, image. And mouse brain tubulin network slice can be identified as shown here, and also axon of a nerve cell from Kasai group of University of Tokyo shown here. And SEIG intensity from stimulated emission microscope, we can relative intensity change of probe intensity by induced emission of a single molecule shown here. And then we could reach the short noise limit at some in some configuration condition, and by changing the pump microscope pump power, and signal intensity and the signal noise ratio versus probe intensity, we can obtain the optimum probe intensity by changing the power of the probe intensity from about less than 100 microwatt to 1000 microwatt, 10 milliwatt at 1 milliwatt. Then we can obtain 0.1 milliwatt, 1 milliwatt to 0.1 milliwatt is the optimum condition can be obtained. And microscope image analysis is shown here. Gray level co-occurrence matrix analysis of the space correlation among the pixels in the 2D image. Compare 9 GLMC between malignant melanoma against nephews samples. Find out good parameters for identification between them. There are 9 parameters having been studied. This is from the malignant cell and just probed by the photothermal microscope utilizing 405 or 488 nanometer as a pump, and then we can obtain the histogram of 9 calculated GLCM parameters. And then from that statistical analysis, set the calculated mean of data as the Gaussian peak and set the standard deviation to be the Gaussian width, set to be searching as a Gaussian width, and overlaps between distribution of benign and malignant tissues. Sensitivity is through positive rate measure the proportion of positive that are correctly identified, namely the proportion of those affected who are correctly identified as having the condition. Specificity is through negative rate measure the proportion of negatives that are correctly identified, namely the proportion of those unaffected who are correctly identified not having the condition. True negative is correctly identified negative, false positive is identify negative as positive, false negative correspond to the identification positive as negative, and true positive is corresponding to the correctly identification of positive. And the statistical analysis in terms of this distribution and nephew cell, the mean, and malignant melanoma mean, and also distribution with some stochastic distribution of the study. And then we can identify false negative, and utilizing ROC character curve. Then ROC is sensitivity to positive plotted against false positive, which is equal to 1 minus specificity is equal to the proportion of the units with a non-negative condition for which predicted to be positive. ROC closer to top left is effective. Area under the curve, AUC criteria of effectiveness of discrimination between malignant melanoma and nephew cell. Correlation good for high sensitivity. And also Uden index also can provide some pointing. Uden index is defined as a pointing maximum or difference between therapy, and this can also be utilized for the identification of malignant cell. And the area under the curve analysis is shown here. In case of 4-5 nanometer pump or 488 nanometer pump, then the all 9 parameters of listed here, and among them, in case of 4-5 nanometer, these 3 contrast, entropy, and variance are give the higher value than the others. And for 88 nanometer, prominence, shade, and variance provide higher values than others substantially. And then from the AUC values of 9 GLCM parameters, it can be concluded that entropy, contrast, and variance are most suited for the discrimination between malignant melanoma and nephew cell in 4 or 5 nanometer excitation. And prominence, variance, and shade are most suited for the discrimination between malignant melanoma and nephew cell in 488 nanometer excitation. Reasoning of the best discrimination parameters between nephews and malignant melanoma is for 5 nanometer morphology and distribution change of hemoglobin associated with cell cancellation. And for 88 nanometer pump case, morphology and distribution change of melanin associated with cell cancellation may be effective. And this is, I like to summarize. We have developed microscopes with PT and SEIG and Cypher models, multimodal configuration. Application to mouse brain, muscle, mouse skin, benign and malignant cells, and GLCM gray level co-occurrence matrix analysis, difference and ROC analysis of super resolution image of mouse skin versus cells and malignant melanoma cells for 5 nanometer entropy contrast variance, for 8 nanometer prominence variance shade effective and most effective for identification between nephews and malignant melanoma. And for 5 maybe the indicator of the morphology and distribution change of hemoglobin associated with cell cancellation, and for 88 nanometer maybe the effective because of the morphology, it represents the morphology and distribution change of melanin associated with cell cancellation.
Okay. So, thank you very much. Even though it has been recording and it's been a pleasure to listen to your recording, we have now the possibility to ask questions to Takayoshi Kobayashi. Are there any questions?
So I have one question regarding the use of ring aperture or circular aperture, which improve the spatial resolutions compared to conventional photothermal microscopy. But how is about the signal to noise? So how signal to noise of photothermal get affected by using this aperture?
So we currently don't see Professor Kobayashi. So I'm not sure if everything still works because it's late in the evening already. So.
Yes, I can see you. Can you see me? And
yes, perfect. Thank you.
So of course, there's a kind of trade-off for obtaining the good signal-to-noise ratio. In terms of signal-to-noise ratio, then the by introducing the aperture, then it inevitably reduces the probe light. However, of course, in case of at first, in case of biological sample, then we easily damage sample in microscope observation experiment. So we must reduce the intensity, and also by optimizing the internal and external radius of the ring structure, we can optimize. We have not yet done in full detail. However, there is some condition. Signal-to-noise ratio is the best in terms of both the photothermal imaging and resolution.
Okay, thank you.
Other questions? In case this is, well, if this is not the case, I would have a short question. You showed these nice results on the amyloid beta imaging, and I was wondering what was the actual absorber for these structures. Well, I missed that maybe to produce the photothermal signal. So what is absorbing, or what was the laser light that is absorbed?
Amyloid beta usually does not have strong absorption, but because of the high sensitivity, it has some dark gray. And also the refractive index change introduced by the existence of amyloid beta in the brain, then it will induce some kind of not real photothermal, but some kind of diffraction-induced change of the probe light.
Okay.
We can utilize this kind of effect. It is a scattering induced photothermal. It may not be appropriate to use thermal, but it is a kind of scattering.
Okay. So what was the pump wavelengths in that case?
In that case, we utilized. Let's see. Could you go back? Usually we use page 13. It describes pump is 488 nanometer, probe is 660 nanometer. In this case, of course, we can change to the appropriate condition depending on the material to be studied.
Okay.
And also to obtain the depth resolution, also another other wavelengths may be even better because of after passing through the focal plane, then some kind of elongation in Z direction, but we can optimize by utilizing this ring structure, controlling the structure of the focal range.
Okay. Thank you. Are there more questions? Please raise your hand or.
Okay, maybe I will ask one more question.
Okay.
So about the balance detector to reduce noise, to improve signal to noise. I'm just wondering that the lock-in, if we modulate at high frequency, then lock-in should be able to remove or reduce the noise to gain the signal to noise. So what I see that by using the balance detector, you have a really high improvement in the signal to noise. So
yes, not, of course, locking amplifier is very popular. We can use and we are using. Together with locking amplifier, we are using balance detector because they have common noise, and also sometimes this noise is fluctuating with time because of biological material. Then the laser irradiation to study, microscopic study, then we are exposing pump light and also probe. Even though probe is weak, but still it provides some kind of heat. And then gradually it changed. And also biological system is, in a sense, very fragile. So they must be as weakly as possible to excite by pump and also probe. So to do that, then we like to reduce the common noise by balance detector. And we are, as I showed you, it is appearing in page yes, page 14. It reduce a lot of noise by balance detection. And this can be adjusted for each sample. It depends on sample, not unique. So we must adjust in real time to adjust to the balance detection.
okay, thank you.